Not everything can be integrated. So sometimes all we can do is approximate our answers with what's referred to as numeric integration. And for the most part, that's what we started out our course doing. We approximated the area underneath the curve using rectangles and trapezoids, and we realized if we increased the number of rectangles, we got a more accurate answer. So using left endpoint rectangles, right endpoint rectangles, trapezoids is one way to do it. There's also the midpoint rectangles that we talked about before. Now, down here in blue is an example of a function that does not integrate. So how would you go about evaluating this answer or this definite integral here? Well, if you can't integrate it, there's no symbolic way to do it to get an exact answer. But what you could do then is to estimate it using the left endpoint, right endpoints, trapezoids, midpoint rectangles, or what's referred to as Simpson's rule, which we'll be talking about shortly. Now, we had talked about trapezoids before. That's basically approximating your curve with a first-degree polynomial because the top of your trapezoid on your curve there ends up being a straight line, which is linear. Lines are degree 1. Now, Simpson's rule basically says I'll get a more accurate answer if I use a second-degree polynomial, a curve. Simpson's rule, which is sometimes called the tangent line approximation, is you take 1/3 how wide your rectangles are times your initial height, 4 times your next height, 2 times your next height, 4 times the next height, 2 times the next height, and so on until you get to the end, but you only go your final height, not multiplying it by anything. Simpson's rule only works with an even number of divisions. So the number of rectangles you would try to put in there, or trapezoids, always has to be an even number. Now another way you can get Simpson's rule is it's just 1/3, and then in parentheses 2 times the midpoint estimate plus your trapezoid estimate. Your trapezoid that we've talked about before can be summed up in it's half the area of the first trapezoid plus all the other trapezoids plus half the area of the last trapezoid, all multiplied by your width. Or some people prefer to look at it as the first height plus the last height plus double all the other heights, all multiplied by half the width. Well, let's go ahead and approximate this using our calculators. So put sine x over x into your y equals. We're going to approximate it, our definite integral going from 0 to 1. Well, to do that, and we're using 10 subintervals, we're going to use our calculator programs that we were programmed earlier in our course. Now, if we plug in 0 when we run our program, it's going to give us a divide by 0 because it's going to try to put 0 in here, and you know you can't divide by 0. So for the most part, we're going to go ahead and try to fool our calculator. We're going to put our lower bound in being 0.0000001, with our upper bound still being 1. Our number of divisions is still 10. When you do that, you should get your right endpoint to be this, your left endpoint to be this, your trapezoid to be this. By the way, if you didn't get that, make sure your calculator's in the radian mode rather than the degree mode. Now, some of you have modified your program so that you get also midpoint rectangles. Midpoint rectangles, you would get this right here. Well, now that we would have your trapezoid and your midpoint rectangles, we can go ahead then and plug it into this formula here to estimate Simpson's rule without having to do it by hand. So we'll go 1/3 times 2 times your midpoint plus the trapezoid, which is up here in green. Then we'll go ahead, we'll type that into our calculator, so Simpson's rule ends up being this here. Well, we now have a submarine. underneath the polar ice cap. We have right here the time going across in hours. Underneath we have its velocity recorded at each hour. Over here on the far right we have a graph of what's going on. Well, you should remember if we're trying to estimate our distance, distance is just area underneath your curve for a velocity function. We don't have an equation for this curve, so we're going to approximate it using Simpson's rule and the trapezoid rule. Well, the trapezoid rule is given to you here. It says take 1/2 your initial value, which is 12, and then you got to double all your other heights. The next height is 14, your next height is 17, your next height is 21, your next height is 22, as you see up here, just going across for your velocity, which is your height on your graph. And then we get 21 again, then it drops to 15, then it drops to an 11, then it drops to an 11, then drops to 14. And remember, it's your first height plus your last height, and then double all the other heights. So here for your last height, we don't want to have that in the parentheses to be doubled, so it's a 17 outside there. Then we said all multiplied by your width. Your width is how far apart these are time-wise, and each one of these increases by an hour. Well, you can do all this in your head, or you could be lazy like most people and type it into your calculator. And we get approximately 160.5 miles. We're also going to approximate this with Simpson's rule to see if we get about the same answer. Here's Simpson's rule. It's 1/3 times your width. Once again, how wide are our intervals? 1. So that's why we have a 1 here. Simpson's rule says your initial height, which is 12, then 4 times your next height, plus 2 times your next height, plus 4 times your next height, and so on. And once again, our heights that I'm uncovering here are the velocities, because on your graph up here, how far up you go is your velocity. So we'll just continue to do this here. After our 21, our next height is 22, our next height is 21, and so on. And remember, what's in front, you got to alternate from timesing by 4 to timesing by 2 to timesing by 4 to timesing by 2. And you keep doing that, with the exception of your last one, which you don't do anything to, because it says it's just that last one, just like the first one is all alone. Then you got to multiply all that out, and I'd recommend your calculator. You multiply it all out, and you get something really close to 161 miles. Your trapezoid and Simpson's rule are both good ways to estimate the area underneath your curve. Sometimes you can get more accuracy by increasing your intervals, but here on this problem we would not be able to because we don't have any more data for making it smaller than just one interval or 1 unit wide.